Hi everyone, I'm an immunology student here in my final year at the university, and I really like viruses, so I thought that I would come and talk to you today about how we can better understand the immune response in order to create an improved flu vaccine. So the influenza virus presents a really huge threat to humans, and I think that threat is often really underappreciated. It causes bouts of the seasonal flu, which we see each winter. And around 20% of us will be infected with that virus. However, for most of us, it won't cause any symptoms, or else it'll just sort of end up in a week off work, in your bed, feeling a bit sorry for yourself. But for certain groups of people, it results in much more serious illness, resulting in stays in hospital or even death. And those groups include the elderly, children under 5, people with chronic illnesses, or pregnant women. And for these groups, as you can sort of tell, these are the more vulnerable groups in our society. And unfortunately, up to 600,000 of these individuals die per year as a result of the flu. Now, to put that into perspective for you, the current coronavirus, which is causing mass panic, has killed just under 3,000 people so far. And to make matters worse, the influenza virus can also result in sporadic pandemics. Now, these are a lot less frequent, but they're much harder to predict when they do occur, and they also tend to have a much higher death toll than seasonal flu. Now, if anyone's seen the film Contagion, it's one of my favourites, the plot of that film is that basically a virus or a viral pandemic results in nearly sort of the whole of humanity being wiped out. And guess what? That virus is a variant of influenza. But pandemics aren't just restricted to fiction. The Spanish flu, which occurred at the end of World War I, resulted in the deaths of 50 million people, which was actually more than the war itself. But I do have some good news. There is a flu vaccine available, but it sucks. And the reason for that is because of the type of immune response that it induces. So if you can have a wee look at this diagram here, this first panel shows what happens when the virus infects us. So the little yellow blobs, those are the virus. And basically we breathe these particles in. They travel through our airways down into our lungs, where they infect the cells that line the lung. And that ends up in the damaged sort of red, as you can see here in the diagram. And that damage to the lung is what causes the flu-like symptoms that are experienced. Now, the vaccine aims to provide protection to that by inducing a type of immune cell called B cells, which are the blue cells up there. These produce antibodies, which are the Y-shaped molecules that's sort of spouting out. And these antibodies are able to recognise structures which stick out of the viral surface. The antibodies bind onto those structures, and then that inhibits the virus from entering our cells, so they can't make us sick anymore. But where the vaccine fails is that the virus is able to change the structures that are recognised by the antibodies, so they can't see the virus anymore, and it goes back to being able to invade our cells and make us sick. This means that the vaccine doesn't offer long-term protection like other vaccines do. And as a result, it's got a really, or people have to get revaccinated annually, and it's also got a really low efficacy, which you can see in this graph here from the CDC. So along the bottom, we've got the different flu seasons, and then up the side, that's the percentage efficacy. So that represents out of all of the people who were vaccinated, how many of those people actually were protected from influenza. And you can see that it often doesn't even reach 50% efficacy. And as well as that, the vaccine offers absolutely no protection against those pandemic strains that I spoke about earlier. So researchers are working really hard to try and fix this problem. And one way they're doing this is by seeing whether we can induce a different type of immune response to provide better protection. And one cell population that they're looking at are the T helper cells. Now, these are the sort of mediators of the immune system. And unlike B cells, they can recognise the virus even after it's mutated, meaning that they can provide much longer term protection. They also form a protective population in the lung after you've been infected, so they're perfectly poised there to provide a more effective and rapid immune response should you be reinfected with flu. But how do they actually offer this protection? Well, you can think of the immune response to influenza like an orchestra. So you've got all the different sections that consist of different cell subsets. And within these subsets, you've got key players, which are all playing a really important part in the response to flu. But without any guidance, the result would be an absolute mess. So you'd have different sections playing out of time, or some wouldn't even know how to get started to begin with. And so in comes our T helper cells. They play the role of the conductor in this scenario. They're able to coordinate the immune response to give a more harmonious response that can effectively rid our bodies of the virus. So T helper cells present a really promising candidate to induce through vaccination, as they're able to induce a more rapid, effective response to flu, which can recognise the virus even after it's mutated. However, we still don't know the steps leading to the production of this population. So I did a little bit of work on this in the McLeod lab for my honours project. We know that the T helper cells must get some kind of signal in order to produce the protective population. But I worked on sort of identifying which cell type could be given this signal. So we know that early on during an influenza infection, the T helper cells actually send out a signal to a type of first responder cell called macrophage. And that alerts them early on that influenza is here, and they can act really early to clear the virus before it spreads too far. So I wondered whether the macrophages were maybe signalling back to the T cells and instructing them to form this protective population. So to look at this further, I infected mice with influenza and then gave them a treatment which blocked the receptor that macrophages use to interact with T cells. And this would block any interactions between the macrophages and the T cells. And I inferred that cells which are close together are more likely to be interacting. So therefore, I hypothesised that by blocking any potential interactions between macrophages and the flu-specific helper T cells, the distance between the two groups of cells would increase. So to look at that within the mice, I sectioned their lungs into thin slices, and then I used a special type of microscopy which stained the different cell types different colours. And I could then visualise these sections under a fluorescence microscope. But how did I know which cells were flu-specific T helper cells? Well, I used a genetically modified mouse model called the trace mouse. And in these mice, their flu-specific T helper cells permanently express a fluorescent protein after they've been activated. So basically, they light up green. And then they're really easy to find afterwards once you've sectioned the lungs. So you can see that here in practice. So these are my microscope images. On the right, that image there is from an infected mouse which was given the block to their interactions. And then on the left, we have a control mouse which was infected but wasn't given an interaction block. And basically each different cell type stains a different colour. So in orange, we have the macrophages. In green, we've got the flu-specific cells, which were the ones that were genetically modified. And then the T helper cells are in red. And where we have the red and the green together, you have a flu-specific T helper cell. Then in the boxes, you can see where the macrophages appear to cluster with the flu-specific T helper cells, indicating that they're potentially interacting. But you can't make any conclusions from just looking at these images alone. So instead, I made measurements based on the images to calculate whether there was any statistical difference in the distance between the two cell types after the treatment. So the first measurement I made to do this, I measured the average distance between each flu-specific T helper cell and its closest macrophage. And this is the graph for that here. So up the left, I've got the average distance, which is the measurement. And then along the bottom are my 3 groups of mice that I had. So in yellow, we've got uninfected mice to compare to the treated mice. Then in red, I've got those mice that were infected but weren't given the receptor interaction block. And then in blue, I've got the infected mice that were given the receptor interaction block. And then the stars up the top represent statistical significance between two groups. So this basically means that the mice which were infected but didn't have their receptor interactions blocked, the flu-specific T helper cells in those mice were significantly closer to macrophages than in the uninfected mice, but there was much less evidence of this in the mice which were infected but did have their interactions blocked. So following on from this, I took a second measurement. So I measured the percentage of flu-specific T helper cells that were close enough to a macrophage to indicate that they were interacting. So again, the graph similar layout here. So I've got my measurement up the side on the left and the same 3 groups along the bottom. And what's interesting here is that in the mice which were infected but not given the receptor block, more of their flu-specific T helper cells were within that interaction distance of a macrophage than both of the other groups. So this means that by blocking the receptor on the macrophages, which they use to interact with the T cells, less flu-specific T helper cells were close enough to a macrophage to be interacting. So this means that under normal circumstances, these two cell subtypes are interacting. And since we know that the T helper cells need some kind of signal in order to form the protective population, these findings indicate that that key cell subset could be the macrophages. So they're definitely interacting with the T cells early on, and it could be that they're providing that signal which then pushes the T cells towards forming the protective population in the lung. And these can then go on to provide protection against a secondary influenza infection. So this work identifies the macrophages as an area for future work to identify the exact steps which are needed to form the protective T cell population. And if we can identify these requirements, this can go on to instruct vaccine design. Now, a number of elements of vaccine design can be altered in order to induce a specific immune response. And if we can fine-tune these details, then we can create a better flu vaccine which induces a T cell response to provide that long-term effective protection rather than relying on the current ineffective option that we've got. So I'd just like to thank everyone in the McLeod lab who helped me during my project, and also all of you guys for listening.